After every subject, there is a moment where people can ask questions. So you can put your question in the chat, and Sean will answer those questions. Besides that, yeah, I think Sean, that we can start with your presentation about machine vision. I'm very excited. I hope everyone is, and I think everyone is. So the stage is yours, Sean.
Okay, thank you, Chris. Hello, everyone. Good afternoon. Thank you all for joining. My name is Sean Leuving. I'm the CTO of Smart Vision, and I'm going to talk about data and annotated data. So what I'm going to tell you is about how we work with limited annotated data and how we still solve real-world problems. In between sections, I will answer some questions and go from there. First, some background for myself. I started in 2003 and Siemens Mobile. I started working on computer vision already. This is one of the first smartphones. This is a Symbian device. This is the Siemens SX1. And what we did there is one of the projects was a mosquito game where we used computer vision, like simple edge detection and the camera and some motion sensors to detect and shoot the mosquitoes. Pretty fun project. It was one of the first. This, for example, this mobile device had a 120 megahertz processor, and it had also 60 megabytes of RAM. So that's nothing compared to what we have now, of course. Afterwards, I joined Napoleon. I wanted to do more with computer vision, so I started doing license plate recognition. My role there was, it was early 2000s. My role there was to port the software to different devices like DSPs or ARM processors, mobile devices, edge devices, and so on. Everything you see here is done with traditional computer vision. So it's still done with some simple neural networks, but also some edge detection. So it's pretty fast. Afterwards, I got the opportunity to work with Daisy Analytics and improve my computer vision skills. We had some fun projects. This is one of them. This is the roundabout counter. The objective here was pretty simple. We want to know the origin of the vehicle and the destination of the vehicle. But we found out that there are a lot of persons driving in the wrong direction. This was pretty interesting. Everything you see is built with traditional computer vision. So it's not part of the deep learning era. So it's using foreground detection and some simple tracking. It's a fun video. It was a fun project. What we also did at Daisy Analytics was work on the Beware project. This was a big project with a lot of companies, where the objective was to create situational awareness for security companies. At the time, security companies had many video walls and looked at video screens throughout the day and picked up some abnormal behavior. So what we did there was put our computer vision software to the test and use it on cameras and detect vehicles and persons and their behavior. And we constructed some 3D scene of the environment where the cameras were situated to give the security personnel more and better information. In 2014, I got the opportunity to start my PhD at Delft University of Technology. I worked there on model-free tracking. The model-free tracking is that we only get the initial bounding box, so it's the square, the green square to be exact, of an object, and we had to track that object indefinitely. And so that basically means that you have to learn how the person looks, or the object, the fish in this case, and then track it throughout the video. Early 2020, I joined Sensing Clues as a volunteer. This is an NGO organization here in the Netherlands, and they do wildlife classification. They asked me to support them with classification of animals. So what you have here are some beautiful creatures, and we have to classify them as what they are, oryx in this case. Just last month, we joined the Gecko competition, also to classify and count animals. This was a competition hosted by a data science platform, and we got second place there, so it's quite surprising, but also very good. At Smart Vision, we work on developing socially relevant computer vision solutions. So we try to aim and make the world a better place for us, basically. One of the big projects in the beginning was Beware. Smart Vision is, by the way, a spin-off of Dice Analytics. Beware was one of the first projects we started. This is the security-related thing. So we picked our software, built it on multiple cameras, did business parts, and it evolved over time. It's still a project, product actually. Another thing which we are able to do is do fall detection of mobile. This is of more and more relevance these days. This is in healthcare centers where we detected a person falls. And we also have the notion of living circles. This is in dementia where people are allowed to walk through the building with freedom of movement, but with a restriction eventually, because otherwise they can't find their way back. This is called living circles. And we support this context. It's basically tracking over cameras. So we use multiple cameras to infer the location of the person and notify the nurse if she's outside of this perimeter. Another thing we do is bridge safety. When bridges are operated, it sometimes happens that persons or other objects are on the bridge when in operation, which is of course a high risk. So we support here the bridge operator to notify them if there's something odd on the bridge surface. Another thing we are asked to do, this is more of a project, but this is contrabanding, which basically means smuggling in prisons and clinics. So the goal here is to detect if there's odd behavior in the first place, but also would it be nice if we can find the smuggler. And another recent project is that of epilepsy. Here the objective is to detect a seizure. We do this particularly for young children because there are no good ways to use invasive products, like for example wristwatches or something like that. So we do it only camera-based. And we support here the family or the neurologist. So how do we all this? We start always with, we have a stack of software, and one of the main things we have is, for example, image classification, where we just classify the entire image. For example, in this case, we say there are 5 hands. We do object detection, which basically means identify and localize where they are. In this case, hands, but we do the same thing for persons and vehicles. Then we have semantic segmentation. In the healthcare, for example, we do this to anonymize the persons, but this basically means this is a step further than object detection. We tell which pixels belong to an object. And with instance segmentation, we even divide the pixels which belong to an object or to a class to the identity, so the real object, unique object. And we work on pose estimation, which is even a further specialization, and we know where the head and where the tail is. For example, in this case, the red dot is the head of the chicken, and the green is the tail. To further analyze and create events, we use tracking, which basically means over a sequence of images. So for frames in a video, we do some tracking, and we try to locate, and in this case, the hands. If you put everything together, we have, this is an example of a care software, it's in Dutch. What you see on the top is this red trapezium, and that says in bathroom. This is the classification task, so we classify what is happening in the image. For example, this is our bed. We do object detection, which is this blue box with a person on it. And we have this pose estimation. So this is everything combined in a sequence. Right. So this is all related to single images. What we want is to do this with true video understanding. What basically means is that we try to understand the behavior of objects in the video over time. So what we want is to detect and understand what's happening in the video. The problem is not only that you have to identify what is happening, but you have to also identify the time at which it starts and what it ends. So the blue bar at the bottom is the total time of the video, and the green bar is the action. In this case, it's typing. So you have to first detect the starting point and make a video clip and do the detection. So it's typing in this case. And that's our input. So our objective, if you summarize it and generalize it, this is actually an objective for entire computer vision field. That is what is happening in the image of video, where, when, and eventually why. And the more you know, the more you can support them in the future. So an example of this objective is that this is a case we do together with the partner. You see the barriers are closed. You see it at the top and at the bottom. So the bridge is officially in operation, but there are still persons walking around, which should generate an alert. This is a hard problem simply because it doesn't happen a lot, fortunately. And so this is an incident which should be reported, but it doesn't happen often because you're not allowed to come in. Another thing which is also hard to detect is contrabanding. This is an example where someone throws over something off the walls of a prison. This is also hard because it doesn't happen often. So how do you create software or detection of events that don't happen very often? Let's take a step back first, and I want to tell something about deep learning because it's the foundation of all the things you previously saw. In the realm of artificial intelligence, everything with robots or machine vision or computer vision or any kind of smart software or machine is incorporated. Within this domain, there's machine learning, which is our algorithms which learn from data. Within this realm, there's neural networks, which is a specialization, a specific algorithm, which is called a neural network. And within this, there's a specialization again, and this is deep learning. So basically, deep learning means it's a deep neural network, and deep is still arguable when it's deep. So what is it? Say we want to classify a banana, we want to say what kind of fruit this is. Well, this is a banana and orange. Then we have some data. This is our neural network. What's relevant is the input and the output. The hidden is the more hidden layers you have. So every column is a layer. The deeper the network is. The output will be then a classification block in this case. So we want to know if it's a banana or if it's an orange. So this is basically, in simple terms, a deep learning network. Since 2014, deep learning has changed the world significantly. Now what you see is that at a certain time, the traditional machine learning algorithms, also the older neural networks and support vector machines, for example, didn't really improve the performance of the software. So with the coming of deep learning and the rise became of the availability of general purpose GPUs from NVIDIA particularly, there was a rise in datasets. In this case, in 2014, it was ImageNet, where millions of images were made available for training. And at the time, also, the learning methods for neural networks became more common and better. So we see the performance of deep learning networks still improve. This is also what we see now. The bigger the network gets, the more data it consumes, but the performance also goes up, still goes up. There's always a but. Deep learning models are data inefficient. What that means is to improve performance, you have to have a lot of annotated data, which is really a problem because there is a finite amount of labeled data. We need to solve this problem with the annotated data because there's a lot of data still coming in. For example, in YouTube, in this case, 82.2 years of data, video data, is uploaded every day. That means a human has to spend his entire life to just watch what's uploaded today. So that's a ridiculous amount, and algorithms have to process this. Another thing is that the number of cameras is still increasing. We have 45 billion cameras at the moment, estimated of course. And this is mobile phones, but it's also security cameras, cameras on your car. There are so many cameras. Security are 770 million cameras, which all have to process in real time usually. And of these security cameras, 54%, so it's 450 million, are only in China. So we need to solve this data problem. There's a lot of data still coming in. And of course, this data is not annotated, so it's really limited. So we want to learn something from the data. This image shows a little bit the difference, that we only have a small part annotated. Of course, this is very arbitrary, and probably is the annotated dot really small and available data a lot larger. But we have to do something about this gap, this difference. The problem is we can't label everything in the world. And it's so much data we cannot do it. So we have to find different ways to solve the data problem. Particularly in video understanding, which is our main goal. A lot of cameras use video, TikTok, YouTube, everything is video nowadays, and also in security and the missions we have as smart vision, it's all video. What we have now is the algorithms we have rely on available data. That's what I showed as well with the pose detection, with object detection. So we currently use a lot of data to train our neural networks, or deep learning networks. So our video understanding is basically limited because we only use object detection, pose, and so on. What happens in research is that we can push this boundary of available data. In research, new data sets are created, new techniques are developed, and so the state of the art currently is improving the video understanding. So we know more and more of what's happening in the videos. But we still need a lot of data. So what we eventually want is basically we want to reduce the amount of necessary data, and also available data maybe, but we want to maximally understand that video. So our goal is to be on the top bottom right corner of this plot. Our goal is to understand more in the video without any data. But this is a paradox, because the harder it gets, the more data we would like to want. So the more we want to understand, it's also harder to get the data. And I'll give you some examples. A simple example would be stealing a bike, or for example, the contraband you just saw. Another video, this is pretty trivial for image detection. We can see a mattress, we can see a knife, and we can see a girl. So she's operating. So our fall detection software would not capture this incident. If you want to have data with exactly this incident, this is really impossible. That's why it's a hard problem we have. And we are not able to collect more data for these hard to detect scenes. So how are we going to fix it? Well, step one, my suggestion is always get more data. This is also hard, but we should always try to get more data. If this is in medical imaging or anywhere else, we should get more data. The reason for this is because you also want to know if you generalize well. So you need more test data, you need more train data. Although it can be hard, we should always aim for this. Before we go on to learning, which is the next phase, are there any questions so far? I can't see any questions, so I'm going to continue. I'm going to explain supervised learning, which is the main learning paradigm at the moment. What we see here is a 2D plot. On the x-axis we have roundness, and on the y-axis is length. We do the same technique. We use bananas and oranges. And the first step is that the human has to label all these data points. So each gray dot is actually a measurement of roundness and a maximum length. So first he annotates all the oranges, and then he annotates all the bananas. What happens then is that the classifier is trained with all the data points. So each dot here, each fruit is a data point, and it learns a classifier. This is a decision boundary, which basically is the separating line into the space between the objects. What you just saw is that a user has to annotate or label every data point. So we want to limit that. So how can we limit supervision? The suggestions I'm going to give is that we want to generate more data. So if we don't have any data, let's generate it. Then we can do that using game engines or using generative neural networks. Come to them in a later point. Another option is to use semi-automatic methods. Then we assist the user in a way that he don't have to annotate all the data points. We can do this by pseudo-labeling or active labeling. For video, we also have point annotations. Another pretty new concept is meta-learning, which basically means that we want to learn faster. So we want to know, with less data, use more learning capabilities. An example is few-shot learning, the zero-shot learning, and then currently there's a hype around self-supervised learning. Let's start with generate data. So what we have is, again, this situation where there's a lot of data and little annotated, and now we're going to generate more data. So what we're actually doing is go outside of the circle and create more data and directly annotate it. We used this in the Beware project already in 2007, where we used a game engine to detect or to generate moving persons. So we want to do some crowd analysis, persons crossing each other, and so on. As you can see, the image quality is pretty lousy, so we only used it for the upstream task of foreground detection, what basically means where an image is motion, and we used it for tracking. Because of all the persons moving through each other, it was a difficult task to track the persons. We could play with illumination, we could play with the shadows, we could also play with the number of persons and movement speed, so it was quite interesting. This was already 14 years ago. Right now, a lot of new data is generated with the game engine of Unity. Unity is used by many games at the moment. I don't play a lot of games, so I don't know that much. But the quality is really superb, as you can see in this image, also many later. But what you can see is that if you can generate an image with high quality, you can basically simulate all the data. You can simulate object detection, so for example, what is the 2D representation of the object. But you can go even further and determine for each pixel to which object it belongs. So it's really accurate. So I'm going to zoom in on the shopping center. So this is a generated image, which is really of an awesome quality. On the right, you see this instance segmentation. So you can see which pixels belong to the boxes. On the center, you can see the object detection with the levels, and you can see also the details. So it's pretty amazing. And this is really useful to progress and generate data in an easy way. The only limitation for these problems is that it's also hard to start somewhere. For static images, it's pretty easy to render in Unity an image, but for video, for a complex scenario like contrabanding or to go with the mattress, it's pretty difficult already because it's a lot of work. What you also see, and this is especially for self-driving vehicles, is the use of one-touch auto. These cars also look pretty realistic, so they can transfer these cars to real roads. Just copy and pasting, basically. What you see on the right is the semantic segmentation, so that's basically the class of each image. The purple one is, for example, the roads, and the dark purple ones are the cars, and so on. Another current option is that of the generative adversarial networks. What we call deepfakes is all done with generative adversarial networks. So I'll now try to explain what a generative adversarial network is. I've done, for sure. It is something to generate something. So that's the generative part. So we want to have a neural network which creates some image we want. For example, we want to create a face. But how does this generator know if the face looks realistic? I mean, that's a hard problem. So therefore, we have a discriminator. The discriminator is also another neural network which tries to predict if the face that is generated by the generator is real or fake. So we have some real faces on the top, and then the fake face on the bottom one, at least the fake face. And the objective of the discriminator is to just tell me if it's real or fake. If it's real, no, it's okay. If it's fake, the entire process is learned. So basically, the discriminator gets feedback from it's fake, and also the generator gets the information that it's fake, so it has to try harder. So basically, they're battling against each other. The generator is going to improve to make it more realistic, and the discriminator gets better at determining what's real and fake. So it's a competition in place. The input of a generator is random noise, so it every time it generates a different image. So we can use it to generate images. An example from the website which face is real is these two images, and we have to determine which one is real or fake. It's too bad that I can't see anybody. These ones are both real actually. But we can do it again. This one is a little bit harder. These are also from the same website. You can see which is real or fake. It's really hard to tell. So the real is fake. It's pretty impressive what a neural network can do, even with high resolution images. So in this way, we can create faces, for example, but other kinds of images as well, with a high quality and high resolution. All right, so this is the section about data generation. Are there any questions so far? No questions? All right, we'll continue. Then I'm going to continue with the semi-automatic methods. So what we want to do here is assist users or make it easier or limit the amount of supervision. So we have this starting situation again, lots of data, we're all annotated. And now we want to selectively annotate images. We don't know which one, but we want to find the most informative data. An example is pseudo-labeling. This is again similar to the supervised setting, where we have these bananas and these oranges. These are already user selected, so the user has 3 oranges and 3 bananas selected, and the classifier is trained with the decision boundary. That's not a lot of data, so the gray is unknown. So we let the classifier now predict on all the gray dots from give me some answer of what is what. Now the classifier gives a high output of the oranges on the right, those 2, and the bananas on the top left. So it's absolutely sure that's a banana, and on the other side it's absolutely sure that's an orange. So this is called pseudo-labeling, so we let the algorithm decide what the labels are, and because we have new data, new annotated data, we can retrain the classifier with these new data points. And we can do this over and over. This is called pseudo-labeling, and it definitely improves the neural network. We also have active learning, similar principle, only now we want to involve the user. So we have a human expert level, that human expert, which labels the hard data points. Human expert. The hard data points are the ones where the classifier doesn't really know if it's banana and orange. It's really in doubt. We can relate that to the confidence as well. But we let this human expert, we let it annotate those hard symbols. These are usually close to the decision boundary. For example, these 2 oranges are pretty close, and these 2 bananas are also pretty close. It doesn't have to be a lot, but as long as he annotates, we get more data, and we can retrain the classifier, and it will always improve. For video, we have this point annotations. The principle is the same. We rely on an object detector. So what you see on the left in the box with generate proposals, the blue, I don't know what it's called, cloud, more or less, is are objects. And these are all the objects in the image. For example, you can barely see, but there are all persons in the street. So all these blue boxes correspond to a person over time. On the front, you see the first frame of a video, and at the back, you see the last frame of a video. These blue cloud thingies are the intermediate frames with the detections. So what we want is this point supervision, which is on the right. We want a user to say from, hey, I want to click on one bounding box and tell me that that is the action. For example, skateboarding in this example. So he clicks with one mouse click on the person who is skateboarding in one single frame, and this is fed back through this action localization training phase. So we learn basically a classifier which tells which of all these blue streams is the skateboarding, and this is learned and this is tested. So with limited supervision, we can localize the action and train it for a lot of videos. With the semi-automatic methods, there's one big disadvantage, and that is still that if there is an imbalanced data set, it's really hard to get it working. Let's take, for example, again, the bananas and the oranges. If there's only one orange and like a million data points for bananas, it's still hard to annotate them. Right, this is then semi-automatic methods. Any questions so far? 2 questions. I have a question about borderline examples, how to identify borderline examples to give them a specialist label. I will come back to that later when I discuss anomaly detection. If I understand the question correctly, how to identify borderline samples to give them specialist label. Yeah, so I'll just go back to the slide, which is more or less. So this is the borderline examples. I think this assumption is the orange is close to the decision boundary. What usually happens is that we have a confidence range in neural networks. For example, a 1, 100% maybe, if it's really confident, and a 0 if it's absolutely certain it's not. So somewhere in between, like 0.5, there's a confidence doubt. That's basically what's happening here. And these are the ones that are usually hard. To determine exactly what is hard is also a problem on its own. So it's more of an assistant thing. We give an indication to the human expert. But this again is an endless loop. So it's something we can improve. If the network improves, then we can continue and so on. Right? Hope that answers your question a little. I'm going to move on to meta learning and self-supervised learning. A few years ago, a lot of research has been done, not by computer vision scientists, but in other departments, on why and how do animals and humans learn so quickly. And so how is it possible that children take the perception of an animal, even if you draw the animal, it knows what kind of animal it is. So it turned out, we summarized of course, that they learn how the world works by observation and creating context. So basically, all their senses are active from birth. And so in a few months, they have processed millions and millions of amounts of data, more or less, and so they learn these concepts. What's added to that is that they also learn physical properties. For example, if someone is behind or in front of, or like gravity, stuff like that. So we want to apply that to computer vision as well. So the objective of the meta-learning goal is how to learn fast. So how do we learn? How to learn fast. An example of how this is tested and evaluated is to give it a training task, which is called sport set. It's basically a training set, and this is the number of data. And so we only have 3 classes with 2 items for training. Now we have the query set, and that's also small. This is the complete training set, basically. The query set is the test set for this support set. To test if the algorithm works, we have multiple training tasks, also with only a few samples and a few classes, and also the query set again with only a few examples. And to evaluate the learning paradigm, we also have a test task, which also has a support set and a query set. So we're going to start now with fusion learning, based on the previous slide. The definition of a shot here is that it's the number of samples of a class you need in your data. So again, a shot here is how many examples do you have for training. On the left side, you have 2 bananas, so you have 2 shot learning principles, basically. Only a few. We can solve it in 3 different ways. First, we're going to look at the similarity between classes. But we assume that in the case of the fruits, that bananas all look alike. So we can use that, because that's knowledge as well. Then I'm going to look at the learning principle in general, from how can you just learn fast without knowing anything about the data. And then again, if you know a lot about the data, you can use that information as well. So first start with similarity. So what we want is we want to have a measure of how different or how similar these two objects are. We call them positive because we want to compare it with another object, in this case an orange and a banana. To do that we use an anchor. This anchor is something that's fixed and it's not used for training. And we want to create what's called an embedding. And an embedding is just a low-dimensional representation called the fingerprint of the object. To do that, we again have a deep learning network, and these are all the same. So for the negative anchor and positive, it's the same network, and it predicts this embedding. So this is the only math I have, and this is the loss function for training. The objective here, what it says, this math function, is to maximize the distance, the d, of the anchor and the p, positive, and the difference between the anchor and the negative. And the margin is not really relevant at the moment. So what we want is that in this fingerprint space, in the embedding space, we want the anchor to be close to the positive and the negative further away. How does it look? So we have this anchor, which is fixed. We're not going to change that. We have this positive sample. Now we have a negative sample somewhere also in this embedding space. In this case 2D. Now we're going to learn it with this loss function. And eventually it will learn that the fingerprint of a banana, the positive and anchor, should be close together because they look similar. And they push away the negative. Because it's so different, we want to have it totally different color. So this is called a Siamese network. This is how we learn embeddings. This is used often in face recognition, people re-identification, and it's also part of the few-shot learning family. Now we have the learning paradigm where we use all the data to optimize neural network. This is going to be a pretty hard slide, so I'm trying to explain it. First, we make a copy of the network we started out. Then we have the support set, which is basically a training set where we optimize this network on this copy. Then we're going to continue with the test set and also optimize the same network again. But now we know what is changed between the support set and the query set, because gradients. So what we're going to do is we're going to backward propagate, which is basically updating the weights of the original network. So basically, this is a really promising approach. But what really happens is that we try to get a set of parameters in this top left neural network, which is so generic that we can apply it to different support sets and query sets as well. So we want to have a good starting point of the network before we learn something. That's basically what this entire sheet is saying. This is really a promising direction, so it's quite interesting. And this is iterated over and over again. So with different support sets, with different query sets, we try to get a common ground, more or less, between all the support sets and query sets. Okay, now the other simple thing, basically, which we already saw, is working on manipulating the data. This is also part of the few-shot learning paradigm. So if you think about it, and you think about how an orange looks, you can try and come up with other examples of oranges just by fantasizing. They call this hallucination in the literature. And what basically happens is that you generate more data because you know the concept. And this is of course done with this generative adversarial network. So we just create new images and then we can improve or simplify basically this few-shot learning paradigm. On the other hand, if you go from few-shot to zero-shot learning, which basically means we don't have any of the samples in our training set, so we want to predict something what's not in our training set, that's called zero-shot learning. We have the support set, which are all the familiar groups. Then we have this query set, which has a totally different group. There are two ways to go about this. So again, this is the first example, our training set. We do some tricks, and then we use some kind of other feature space to represent it in. So in this example, the text space of Wikipedia is used to say from orange is orange, so give it a name, and a banana is a banana. This label space is quite interesting because it also knows, in the case of the watermelon, where the watermelon resides. Another thing, what's happening, and this is more common, is to use the same principle, also use the text space and the image space, but now use attributes, because the labels can be ambiguous. The attributes usually are not. So if you have multiple predictions for the same object, in this case orange is orange, but there's also round, and the banana is curved in yellow, we can say for my watermelons, for example, round. So this is then meta-learning. Yeah, okay, enough further questions at the moment. There's Q&A. Okay, Q&A I will postpone because these are generic questions. Thank you. So we move on to the revolution in learning. And this is a big buzz because this is self-supervised learning. And this is quite interesting and quite promising as well. It's part of unsupervised learning. And what we do is learn from the data itself and let the data annotate itself. So we give it different tasks. So we have a lot of data, partly is annotated, but what it's able to do with self-supervised learning is use all the data, almost all the data, and have it annotated by themselves. This sounds really interesting. How is it done? One of the first principles was by using masking. There are other principles as well. But you have, for example, an image, and you block out part of the image, and then the neural network has to predict what is missing, what's the missing part. Other examples of this principle is from here we have the column images. We transfer it to grayscale images, and then the image has to predict what the color was originally. And we can do it indefinitely for all the images and all the videos to learn from the data. Another example which is also really helpful is by learning concept is predict occluded from the visible. You have to imagine that this is then again the Dam in Amsterdam, and what we want to do is predict what's behind the person who's walking there. So in a video this is really simple, and since we can use the multiple frames, we can predict what is behind the person. So in a way this is an extension of the previous one, only we now use the temporal, so the video information, to predict what's occluded. Another technique is that of exemplar learning, which is basically we modify the objects in that image so much, or we don't have a notion of objects, but let's say the entire image, and then we modify it so much by using different colors, by using different rotation, scale, and so on. So what you see on the bottom image is on the top left, that's the true image, that's the image. We modify it so much in different ways. So these are all the modifications, and this is an output class. So what the network has to do is predict the original animal based on the artificially generated ones, the data augmentation. Also similar to the previous ones. A big step has been done with the rotation example. This is a pretty popular example as well. So what you have here is we have all this video, all this data, and the only thing the network has to do is predict if the image is rotated or not. So the input image stays the same. We can modify it by randomly rotating it, and the network has to predict or classify if it's 0 degrees rotated, 90 degrees, 180, or 270. And it turned out that the networks are able to really learn concepts of, for example, animals or features, basically, which is really useful for other upstream tasks. Going further, in this similar concept is that we can do kind of a jigsaw puzzle. Principle is the same, only we divide this image now in parts. The 9 parts of the tiger are randomly chosen. They are spatially not overlapping, so they're randomly selected. Then we shuffle them around, and what the network has to do is to reorder them. That's the only objective. In this way, the network is able to recover the image and also learn visual concepts. For video, we can do even more. This is also a harder problem because learning is more complex, but in principle, you can predict the future from the past. The other part is the future, the first axis is the time. And the past is just what we saw. So if some action is happening, we want to predict the future. We can extend it from less data, so only from the recent part, all the way around. So we have now the present, and we predict the past. You can also split the video in half, and so you can make it predict the top from the bottom while the video is playing. So to revisit all the things we just discussed, we had supervised learning to start with, where we learn from the labels. We get medium feedback. We only have, for example, it is an orange, it is a banana. And with unsupervised learning, we only learn structure, so there's no feedback if we have concepts. But with self-supervised learning, because we work on the pixel level, we have a lot of feedback and the networks get really rich. So now I'm going to go over anomaly detection. This is basically we want to determine if it's a banana. So we measure a lot of bananas. We count the number of lengths we encounter, so we have more or less a histogram, and then we get this distribution. The green one is the mean, the average value, and the red ones are the variances. So what we then have is that everything outside of this specific length we call an anomaly. For example, if you have only a banana of length 5 and then length 10 on the other side, on the right side is an anomaly. And also bananas of size 0 don't make any sense. That's the concept of anomaly detection, so we want to use that, and we again start with a generator. So what we now want is this generator has to learn the concepts of the real world. And we also want a discriminator to detect if it's an anomaly based on the input. So we now feed in not the random noise, but the input from the scene to the generator. It has to generate an image. The image is also going into the discriminator to determine if it's an anomaly, so it's basically a classifier, like we just saw. Generator generates some kind of image. The generator has the concept of what the scene usually looks like. It's also fed in the discriminator, and because these both can be compared, we can determine based on the threshold if it's an anomaly. You can identify the location where the anomaly is. What we use currently use a lot is the human loop. So we usually start our own networks with self-supervised pre-training, where we have to learn features of our data, because not everything is annotated, and we just use the human expert to do some active learning. So we look at the harder points and to summarize everything, we started out with generate data, where we looked at game engines and generative adversarial networks. We also looked at semi-automatic methods, where we use the knowledge of expert users to give us feedback. We looked at meta-learning, how to learn fast, and by looking at few-shot learning and zero-shot learning. And at the end, we looked at the promising self-supervised learning to learn from the data itself. And we had a brief look at other methods, alternative methods to solve the data problem, which are anomaly detection and online active learning. So in practice, what I suggest is when data is available, try the self-supervised learning paradigm, because it looks really promising and the data is really burned, the concepts in it. And then we can fine-tune afterwards with the data that is annotated by using meta-learning methods. As a fallback, we usually also use anomaly detection. Think again of the steering of a bike or the girl with the mattress. It's also interesting to see what detection anomaly detection does, because it has more information about it. So that's it. Thank you. Thank you all for attending. I will now answer some questions. Okay.
Yes. Thank you, Sean, for your very interesting webinar about machine vision. I have to say I really enjoyed it, and I think and I hope, of course, that everyone did. For some questions, I think there's still some time for other questions. I thought I saw one already.
Yeah.
So for people who have some questions, yeah, still got the time to ask Sean whatever you want, of course.
Yeah, so I'm going to answer some questions. I have a question here. What are possible ways for data to reduce the high false positive rate? This is again related to a problem with another question, which is the imbalanced data set. What we usually do there with the false positives, we want to try to annotate them as well. That's the best way. This is the active learning part. So either it has a high confidence or low confidence, but basically when you have false positives, the best way is to look at the validation set and look there. And so it's really important to have your training concepts correct instead of learning with less data. If you have a lot of false positives, then also look at your training principles and your validation set. Okay. Another question, how do you define imbalanced data and balanced data? So imbalance and balance is basically that you have the same number of items in one class and the same number of items in another class. So it's easier for a network to distinguish between them. If during training it only sees apples or bananas and doesn't see any oranges, for example, it's really hard to distinguish between them. So that's the difference between imbalanced data and balanced data. We can solve this imbalance by offering the one with the lower number of examples more often to the network, so it sees it more often, and the class that is seen most often, we offer it less to the network during training. That's basically how we do it. And a question here, how is the distance calculated between the anchor, positive and negative? That's a good question indeed. I didn't mention that. There are multiple ways. The simple measurement of distance, because you work in some kind of multi-dimensional space, is just by using the Euclidean distance, or for example the closest distance, cosine distance. Those are basically the two ways of determining the distances. But there are other ways as well, of course. But it's up to you to select. It's more or less a hyperparameter in these cases. Okay, then I have another one. Can a model that has been trained with self-supervised learning be used for transfer learning? Yes, that's indeed the key. I didn't mention that, but self-supervised learning, there is no upstream task yet. So you have to, it's more or less a feature learner. So you learn the principles of features in the data. So it is actually almost always exclusively used for transfer learning. And yeah. I hope this answers your question. Thank you. I think that's it at this moment.
Yes, right. I think all the questions are answered. I hope everything is clear. Once again, Sean, thank you so much for being here, taking your time, of course, for this presentation and for this webinar. Like I said, I really enjoyed it, and I hope everyone did. Thanks to everyone as well for joining us here today, joining this webinar, and hope to see you next time at one of our other webinars. One more thing, the webinar is recorded as well, so you can watch it back on YouTube. So if you have any friends or other colleagues who want to see this interesting webinar from John, it is possible to watch it back. Yeah, and once again, thank you all so much for your time, and hope to see you next time at one of our interesting webinars, or hopefully meetups if it is possible again to do it not online but in real life. Yes. Thanks, John. Thanks again, and yes.
Thank you, Ulrich, and thank you everyone for watching. Bye.
Yes. Bye bye.